In this video and the upcoming videos, we're going to focus on second-order linear homogeneous differential equations of the form y double prime plus p of x of y prime plus q of xy is equal to 0. Now, I generally don't like doing this, but I feel that it is necessary for the purposes of this conversation to begin with a theorem. And this theorem states that for a second-order linear homogeneous equation of the form shown here, it always possesses two solutions, which we'll call y1 and y2, that are linearly independent. Now recall what linearly independent means, is that if we were to come up with a linear combination c1 y1 plus c2 y2 is equal to 0, that equality holds only if c1 and c2 are equal to 0. We can also evaluate their Wronskian if we're not sure. And also, what we can say from this theorem is that the linear combination c1 y1 plus c2 y2 is the general solution of this differential equation. So again, so far we have said nothing about how to actually find the solution. We're just talking about the properties of these second-order ODEs. Now note here that we're saying that we can combine the two solutions, and that too is going to be a solution. And this is what we call the superposition principle. And we can show this to be true. So if we have our second order ODE as such, what we are saying is that c1 y1 double prime plus c2 y2 double prime plus p of c1 y1 prime plus c2 y2 prime plus q of c1 y1 plus c2 y2. And now what we can do is factor out the c1s and c2s. And this leaves us with y1 double prime plus p y1 prime plus q y1 plus c2, and then we have our second function y2 prime plus q, p y2 prime plus q y2. And now note that we know that y1 and y2 independently, they are solutions to the ODE given up here. Therefore, these bracketed terms over here are both equal to 0. Therefore, we have c1 multiplied by 0 plus c2 multiplied by 0, which is equal to 0. So what this tells us is that if we know that y1 and y2 independently are two solutions to this second-order linear homogeneous ordinary differential equation, then their linear combination c1 y1 plus c2 y2 is also a solution, and what we call this is the general solution. Now, to continue this discussion, we can have a look at a very simple second-order ODE. And this will be as simple as they come. So we're going to say the second derivative of y with respect to x is equal to 0. We can readily integrate the above equation. So the first integration will tell us that dy by dx is equal to c1. we can differentiate one more time, which will give us y of x is equal to c1x plus c2. So we know this, that when we have a second order ODE, we're going to have, and we integrate twice, we're going to have two integration constants. What we can do is actually write this solution in general terms as c1 y1 plus c2 y2, where we can say that y1 is equal to x and y2 is equal to 1. And we see that both solutions, y1 and y2, independently satisfy the ODE. So we have y1 is equal to x. If we take the first derivative, dy1 by dx, that is equal to 1. And if we take the second derivative, that is equal to 0. And this satisfies our ODE. We can do the same thing with y2, which is equal to 1. Taking the first derivative of y2, will give us 0, and trivially, the second derivative will also give us 0. So this is a very simple example that shows us that our general solution, c1y1 plus c2y2, can be broken into its component solutions, which are y1 and y2, and each one independently satisfies the ODE as we have shown right here. In addition, you can check for yourself that these two solutions to the ODE are linearly independent.